Good afternoon, everybody. So I'm Arthur, and I'm a PhD student at COSIC from the KU Leuven. And my main research topics are fault injection and side channel attacks. So for this talk, I'll give some sort of an introduction to EM fault injection in general. So this is kind of a combination of multiple works. So for the outline of the presentation, so we'll start with the basics of EM fault injection to more or less explain what it entails. Then we'll switch to the fault mechanism or the fault model that you can achieve with EM fault injection. And then finally, I'll explain a little bit the different designs or the different design parameters that you can play with when building an EM setup. So with EM fault injection, what we try to do is fold a device, so a microcontroller, for instance, by exposing it to an electric or a magnetic field or a combination of both. And there's different ways of doing it. So you can inject a pulsed magnetic field or a continuous magnetic field or EM field. But for this talk, we'll focus on the pulsed variant. So we'll only consider short pulse H fields in this talk. So the advantages of EM fault injection are that you can target only a single portion of the IC. So you can have a little bit of locality. So for instance, you can only target the memory of the IC without exposing the rest of the die to the field. In theory, you don't need any decapsulation. So the EM field will propagate through the packaging unless it's a metal package, which is in contrast to other fault injection techniques. So for instance, with laser fault injection, you need line of sight, but that's not needed with the EM fault injection. It will just propagate through the package. You can have good timing resolution. So if you want, you can target a single clock cycle, provided that your target isn't running over, let's say 200 megahertz, and it can be done cheaply. So for €100 or a little bit more, you can build yourself a decent EM fault injection setup. The downsides of EM fault injection, and as is with most fault injection methods, is that so the behavior of the device is kind of a black box. So you inject an EM pulse into it, it will fault or it might not fault, but you kind of have no idea why or what's happening inside the device itself, or which parts of the logic that are actually causing the fault to occur. And besides that, there is also a very large parameter space where you can play with. So you have your temporal resolution, your timing that you need to get right. And there's also a lot of parameters for setting up the EM setup itself. For instance, for designing the probe that you can play with. So there are many parameters, and all of them will have an impact on the result of your fault injection campaign. And it's difficult to estimate which one you have to tune most or what will give you the best results. So for this talk, we'll focus on magnetic field fault injection because it's the most popular variant. So actually, most of the papers that are published on EM fault injection, they will all or almost all use a magnetic field probe. So, and one of the main reasons for it is that it's very easy to build one of these probes, and these magnetic fields, they couple very well with the metal layers of the IC. So how do you build a magnetic field probe? So they're usually shaped as a solenoid. So here on the top right, you can see the basic solenoid shape. So, and then you can play with a number of windings that they have with the diameter of the solenoid and with the type of material that you put at the core. And some general parameters or the general design space of these solenoids is that you take a core which has a diameter of 100 micrometers up to 10 millimeters even, and you put 1 to 20 windings into your solenoid. Another advantage of using these H-field probes is that you can build them with very high rise times. So the rise time of the EM pulse that you inject can be in the nanosecond range, but so they require very high currents in order to function properly or in order to generate enough power in your field to actually inject a pulse. So the range of the currents is in the ampere range, which puts quite some stress on the components that you use to build the setup. So how does an EM pulse induce a fault? So you generate a short EM pulse. It will couple with the metal wiring inside of your IC. And while it's coupling, there will be voltage fluctuations inside of the metal layers of your IC. And depending on the duration of these fluctuations and their position relative to the clock edge, you will be able to inject a volt. So what you require is that these voltage fluctuations that occur inside of the IC, that they occur around the setup and hold time. So in every IC, if you require your data to be stable around the clock edge on which the data gets sampled, and if you induce these voltage fluctuations around that sample period, you can induce faults. But so the size of your voltage fluctuations, so it's indicated with these two curves on top of the picture here. So they will depend on the properties of the EM pulse that you inject. So if you inject an EM pulse with a lot of power and that resonates over a long period of time, for instance, you can inject a very wide pulse and you might be able to fold multiple clock cycles. While if you inject a very narrow pulse, you will maybe only be able to inject, you will be only able to fold a single clock. So in order to demonstrate a little bit the effect of EM pulses on a circuit and to show the fault model, we targeted Atmega 328P. So this is the common microcontroller that you can find in an Arduino Uno. So it's an 8-bit AVR microcontroller. It's a two-stage pipeline, 32 working registers, some flash memory, some RAM, some EEPROM. And in order to show what is situated where in the IC, we took a true substrate image with a near-infrared camera. And then you can clearly look at the flash memory, the RAM, and the logic. And we did this in order to figure out where or which component the EM pulses actually affect. So then we ran we characterized the device for where it was sensitive to fault injections. So the first thing that you do for a characterization is you put a device in a known state. So you reset the target and you put all the registers in the register file to a certain value. You execute your test code, you inject a fault. So the fault is timed by having an assembly instruction that pulls a pin high. So this is what we call our trigger. Then we have some knobs, and then we have a target instruction followed by some more knobs. And then after injecting the faults, we read out the results in the register file and we start all over. So before every fault injection, we reset the entire device to be 100% sure that it's always exactly the same code that's executed and that there aren't some transient effects left behind from the previous fault injection. And so during the characterizations, we vary this target instruction. So we vary it such that different components of the microcontroller are triggered. So we load some data from memory, we store some data in memory, we do some arithmetic operations to trigger the ALU. And that way we scan the entire surface of the chip. And every time a fault is registered, so every time the register file is read back and it produces a result that we don't expect, so we call the fault, and that way we can build a fault map for the device. And the fault map looks as follows. So you have your picture of your die again, of the microcontroller, and you can see, so every spot that's colored in is a position where, for an arbitrary set of instructions, we were able to inject a fault. So the darker the color, so the more red the color, the higher the probability is that that a fault is injected. So those areas are the most sensitive to fault injections. The blue are the least sensitive, and where there's no spots, not a single fault was injected. So the reason why this figure looks so, why you can attack a single position on the die is because we use a very small probe in this case. So we use a probe with only 100 micrometer in diameter. Which allows you to target very small points on the die, considering that this die is more or less 3 by 3 millimeters big. So now that we know that more or less only the flash memory is sensitive to EM fault injection, we assume that transferring data from memory is the most interesting instruction to look at and to characterize the device and how it reacts to EM fold injection. So that's what we did next. So we use two instructions to characterize what happens if you load data from memory. So LPM means loading data from memory, and we did two things. So we loaded either all ones, FF, or all zeros from the flash memory. So, and the fold results you can see in the figure here below. And so you have your I coordinate and your X coordinate, which is the position over the die. So if you look at the picture again, so this is X, for instance, and this is Y. And then the vertical range, this is the timing of the fold injection. So then you have to read this from the bottom up. So in the bottom, there's time instant 0. And then you go further in time for every clock cycle that you target. So the target device was running at the 8 megahertz. So that means that your clock period is 125 nanoseconds, which is something important to remember. So what we do, we execute our piece of target code, so which means first you have a knob, which is, if it's indicated in blue, that means that we got folds back when we target that particular position at that particular time instant. And then if we get yellow, that means that the device crashed. So it went into an unknown state and it wasn't able to recover from it by itself. It required a hard reset in order to function again. So in the first clock cycle, we loaded a knob from flash, and you see it's sensitive to folds. Next clock cycles, we did a load from program memory instruction. So that's reading from flash. You see again a lot of folds all in the sensitive area. Then there were no folds. And then if you load it all once from memory, once the data should be transferred over the bus to flash, or the bus from flash, there were no folds injected, which is in contrast to when you want to load all zeros from flash, you get a lot of folds at this particular time instance where you expect the data to be transferred. So this means that the fold model for this particular device is set to 1. So every time you inject the folds, if you load all ones from memory, you will never be able to inject a fold because all the bits are already 1, and so none of the bits will be reset. But if you load all ones from memory, then you're able to inject a fold, because the fold model will always indicate that you will always put bits from 0 to 1. But this is very device specific. So if we repeated the same experiment on an STM ARM microcontroller, and there you get exact the opposite effect. So there the fold model it goes from 1 to 0, so a bit reset instead of a bit set, as in this case. So what's also interesting on this picture is that all the folds are injected right around the clock edge, it seems, and the intervals between the folds are nicely 125 nanoseconds. So which means that we're only able to fold the device around the clock edge. So because when constructing this figure, we injected folds in every 10 nanoseconds. So the blanks in between these clusters, they're not due to us choosing an interval, which was exactly the clock period, but just because no folds we were not able to inject any folds in between the clock edges, because we were using such a small pulse to inject the folds. So in the next part of the slides, I'll show how to build an EM pulse fold injection setup. And there you also see that by tuning the parameters of your pulse setup, you're able to manipulate how wide this, for instance, is. So what the range is for the time when you can inject an effective fold. So because here the pulse was so narrow, you had to get your timing exactly right. But if you make your pulse wider, you have a little bit more play, and it's easier to inject an actual fold. So what does an EM fold injection setup look like in general? So just put all this out. So you have your probe, which is here depicted by a coupled transformer. Then you have a switching element, which allows current to grow from your charge accumulating device into into your probe. And then you need some peripheral equipment. So there's a power supply and a triggering device, which allow you to accurately control the timing of your fold, as we saw was needed in the previous slide, and a power supply which ranges up to at least 500 volts, I would say, in order to accumulate enough charge on the capacitor here, and the charge is then switched into the injection probe. So that's the more classical setup. There are many different devices or setups that you can build. Some of them are built around MOSFETs as switching devices, IGBTs. Some people use capacitor as a charge storing device. Some use an inductor. You can even use a transmission line. And if you want to inject EM pulses with a very high voltage, you can also use a gas discharge tube or spark gap as a switch. But then you're within the 1000 volt range, more or less. So how do we model? So when we want to build one of these setups, it's important to have an idea what the effect is of playing with the different parameters, and which parameters you can play with, or which parameters will have an effect on your pulse. So what you have is, of course, you have your solenoid, so your injection probe. That's going to be an important one. Then you have your charge accumulation device, which is usually a capacitor. And then you will have some parasitic resistances and inductances in your circuit itself. So then if you look at the circuit, I mean, many people will recognize them from a basic electronics course. So this is a basic RLC circuit. So if you play with the charge capacitor, the parasitics, and the inductor, you can basically tune the RLC response of the circuit, and thus the shape of the pulse that will come out of your coil. And the shape of the pulse will determine how, and the size of your probe will determine how this thing couples with the device. So next slide. So, and in order to demonstrate the effects of the different components, so the capacitor and the coil and the parasitic resistance, we build a very simple circuit. So, and it's based around a gas discharge tube, which releases all the charges accumulated on a small capacitor over our injection probe. So the injection probe itself, it's a 2 millimeter ferrite core. And then in the basic setup, we just put 2 windings of a small enamel wire around the tip. And we have a 64 picofarad capacitor. So, and we will use a high voltage power supply, which puts 400 volts around the capacitor. And every time the capacitor charges up and goes above this 370 volt, a breakdown voltage will occur over the gas discharge tube, and an EM pulse will be generated. So, and the EM pulse, the response of the EM pulse itself was measured with a 50 ohm microstrip line. So with your small little probe, you scan the microstrip line, and this will give you an amplitude response, and it also will give you an indication of the resolution, because your peak amplitude will occur at a certain distance from the microstrip line. So, and this distance also indicates the spatial resolution of your probe. Okay, so then we characterized, or we varied 3 different components. So the capacitor, the diameter of the ferrite core, and the number of windings. So, and the first thing that we tried was changing the capacitor, and as you would expect, so the bigger the capacitor, the higher the voltage of the pulse that was injected, but also the larger the width of the pulse. So this is the voltage measured with a microstrip line and the time response of the pulse. So then if we change the core diameter, but we keep everything else the same, so use the same capacitor, the same number of windings, then you can clearly see, so the x-axis here is the spatial resolution of your probe, that the bigger you take your probe diameter, the lower your spatial resolution will be. And then the last thing that we varied was the number of windings. So if you change the number of windings, but everything else stayed the same, so the energy that's released by the capacitor will be the same, but your inductance will change, will increase. So the higher your inductance, the lower your voltage will be, but the wider your pulse will be. And so with playing with all these different components, you can shape the pulse generated by your device such that you can target individual clock cycles, or that you target multiple clock cycles at once, depending on your needs. And so in order to demonstrate this, we built a small EM fold injector. So this is a MOSFET-based EM fold injector with a charge capacitor, which is used to accumulate a charge, and this one is in discharge over the solenoid core. So the exact specifics are not really required, but what's important to remember is that we tweak the parameters such that so the capacitor, the inductor, and the resistances here, such that the pulse width was equal to the clock period of the device that we're targeting. So the device that we're targeting was an STM32F4, so that's an ARM M4 microcontroller, which was running at 100 megahertz. And so we tweaked the components such that the pulse width of a single pulse was equal to a single clock frequency, give or take. And so the device that we're targeting was not decapsulated, and the target code that we ran on there was very similar to the one that we ran on the AVR microcontroller. So we load data from memory, and so we load 10 values from memory, and we store them in consecutive registers. And the data that we loaded was 55555, so this 0 and 1 to be, well, a series of zeros and ones in order to be independent a little bit of the full model. So it can be either set to 1 or set to 0. In this case, it doesn't matter. But the important part of the target code is that, so we load data from memory, and every cycle we load 55555 into a consecutive register. So, and then if you look at the probe response and the fault results, so first, so this is the critically damped probe, which is the one where the pulse is exactly the size of a single clock cycle, of the period of a single clock cycle. And then if you look at the faulted or injected, so every clock cycle we load 555 and so forth into a consecutive register. And then if we play with the timing of this pulse, so if we inject the pulse after, at the beginning, then we only fold loading into R1. If we inject the pulse 10 nanoseconds later, then we only hit R0, then we only hit R1, and so forth. So we're able to exactly hit the load to a single register. So we hit basically a single instruction. But if we then change the parameters of our pulse injection setup and we make a little bit underdamped, so you have a little bit more oscillations here, then you can see that you start faulting more than just the single load to a register, and that you actually fault multiple loads and multiple instructions. Here you can see, for instance, that you're targeting 2 consecutive instructions with 1 fault injection. So you see that the voltage fluctuations in the device persist longer than before. So and then to conclude, so EM fault injection can be done easily and cheaply, but it's very important to get the timing right, and the results that you get out of it are also highly dependent on how you design your probe and set up your pulse generator. So thank you, and are there any questions?